All right, good morning. Last week we covered a whole slew of differentiation rules, and I believe on Thursday we covered the derivatives of trigonometric functions. Okay, so today we add another weapon to our arsenal, namely we're going to differentiate exponential and lowercase logarithmic functions. All right, and if we have time, we'll start. Certainly, next time we'll complete a section on differentiating inverse trigonometric functions. All right, so let's start with this. So let's start with exponential functions. So recall if a is greater than 0, then a to the x exponential function and just I may use this phrase. I don't think it's really so standard, so I'll put it in parentheses. Say with base a, and this should somehow be seen as analogous to when you talk about logarithms and you have log base a. All right. Okay, so we have these exponential functions, and we would like to differentiate them. Okay, so we use the verb d dx of a to the x. Okay, and what would the power rule tell us to do? Okay, well, if we use the power rule, right, this would say, oh, this is, of course, xa to the x minus 1. But, of course, there's a problem with the power rule. Power rule said this. Said that the derivative of x to the n was nx to the n minus 1, and we did this for rational numbers, q. Okay, so first, here, the variable is the base and the exponent is a fixed number. And here, the base is a constant and the exponent is a variable. Okay, so this does not fall under the power rule. And so we can't do this. Okay, so what can we do? Well, none of the other rules seem to be of much help to us right now. You know, I don't have a sum. Well, it's exponentiation, but there's not really a product lying around here anywhere. There's certainly no quotient. I don't really have a composition of functions. Okay, so none of our rules work. We have to do what we hate to do, which is go back to the definition. Right, we need to whip out one. Okay. Too bad, so sad. All right, so we know that the derivative of a to the x should equal the limit as h goes to 0. Well, let's see. Well, the function is a to the x, so I replace x by x plus h minus a to the x divided by h. Okay? What could I do with this top bit? I've got to do something, otherwise I'm stuck again. Can I factor? Yeah? No. Yes. What can I factor? A. How many a's can I factor out? How about a to the x, right? I have a to the x here, and, well, I have more than a to the x here, so when I write this as limit as h goes to 0, a to the x times, well, I know this last term is going to have to be 1. Right, what's this term going to be when I factor out an a to the x?
A to the h.
A to the h, excellent. Okay. Now, as far as this h is concerned, a to the x is a constant, right? Because there's no h in there. Whatever I make h, a to the x is just a to the x. So I can pull constants outside of a limit as long as the remaining limit exists. Okay, now, at this point, I'm not going to prove that this limit exists. Okay, I'm just going to tell you it exists. It's a little edict for now. Okay, so let me just say this limit exists. Well, what is this limit if it exists? Okay, we'll see later. But here's what I can say. Right? If f of x equals a to the x, then f prime of x is a to the x times this limit, whatever it is. Okay? And that's just f prime of x, just the derivative. Okay, fine. I haven't said anything new. Okay? And what is the derivative at 0? Well, it's what happens when I plug 0 in for x. So I get a to the 0, which is 1. So I'm just left with this limit. So this limit is just the derivative at 0. So that's nice because now I can, instead of writing this limit, I can just write f prime at 0. Okay. Now, one thing which should be clear is that if I change this a, there's a very good chance that this limit will change. And in fact, it will. Right? If you make a2, you make a3, you make a4, 5, whatever, you get different limits out. Now there's a special place, there's a special number that you can stick in here where the limit will actually turn out to be 1. So, and there's only one number. So if the limit as h goes to 0 of a to the h minus 1 over h is 1, okay, so if this limit is 1, then I can actually tell you what a is. Anybody have a guess?
E.
Very good guess. It's the number e. Okay, so this magical number e shows up as this limit. Okay, so what does that tell us? Well, we know that in general, the derivative is a to the x times this limit, f prime of 0. This limit. Okay? So if a equals e, then the derivative is equal to, well, e to the x times this limit, but if we said if a is e, then the limit is 1. Right, so you just get e to the x. Okay, so this is very nice. So the fact that we've recovered here is that the derivative of e to the x is e to the x. Okay, so this is, if you like, this is, I mean, this limits how you could define e. E is the number such that this derivative actually equals the same function. Right? That it's the same exponential function. Okay, so that's very nice. And what does that mean pictorially? Well, if we draw our graph of e to the x, recall if a is greater than 1, then all of the exponential functions look like this. And we pick a point, say this is a, not to be confused with this a, and I draw the tangent line, that point. Okay, well, the value at this point is, of course, e to the a, because this is the function, e to the x. Right? And what's the equation of this line? Well, it's going to be y minus e to the a equals the slope times x minus a. And what's the slope? Well, the slope is the derivative evaluated today. Of course, the slope, I mean, the derivative of e to the x is e to the x, so it's, again, just e to the a. So this is a rather peculiar situation where the point you get here is actually the same as the slope that you get over here. And no matter what a you choose, you always get this relation. And e to the x is the only function that has that property. Of all possible functions in the universe, it's the only one that does that. So that's nice. Okay? Well, now you have e to the x, and we know its derivative. Well, it's always nice to talk about the inverse function, because remember, if you view e to the x as a function from the real numbers to the positive real numbers, okay, remember we had two very nice properties. It's a one-to-one function, right? It never repeats a y value. And it's an onto function, right? Right? As long as our range here is just the positive real. Because every positive real gets hit somewhere on this curve. Okay? And that, if you had a one-to-one and an onto function, what did we call that? A bijection. Right? And every time you had a bijection, it meant you had an inverse function. And that inverse function is the natural logarithm. Okay? At least it is for e to the x. The inverse of e to the x is natural log of x. And what then is the derivative of the natural log function? I hear pre-knowledge. This is good. It means at least you're waking up to remember. Okay. Well, how do we compute this? Well, here's our trick. Okay, we start with the function y equals natural log of x. Okay, the important part here is, of course, the inverse of e to the x is ln of x. Okay, which means that if I say take e and raise it to the y, this is the same as e to the ln of x. And because these are inverse functions to each other, right, what is e to the ln of x?
1.
I hear a lot of answers.
X.
I hear x, I hear 1, I hear ln of x. Okay? Remember what inverse functions did. Okay? It was like running the tape forward and backwards. I start with something, I run the tape forward, I run it backwards. I'm back where I started, yeah? Okay, so I start with x. I run the tape forward, I run the tape backwards. So I end up with x. Okay. So if y equals ln of x, then e to the y is equal to x. Now I differentiate both sides. Okay? Now when I differentiate this side, I have to use the chain rule. Because I have a function e to the, well, and I have another function up here. So what I'm supposed to do is I do, okay, the derivative of the outside function, e to something. Well, the derivative is just e to something. Times the derivative of the something. Okay? Equals the derivative of x, which is, of course, 1. Okay, well, I'm looking for dy dx. So I divide. And I get 1 over e to the y. But I didn't want y, I wanted x somehow. So let me put ln of x back in. So I get 1 over e to the ln of x. Oh, and we have the same thing as we had above. E to the ln of x is x. So I get 1 over x. Now this to me is a little bit surprising. Somehow, I mean, e to the x and ln of x, okay, these are nicely tied together. You take derivatives of e to the x, you stay in the exponential realm. Right? You would somehow expect, I'm not sure what, that if you differentiated ln of x, you'd stay in the logarithmic realm. But somehow you actually end up in the world of polynomials. I mean, okay, 1 over x isn't a polynomial, but it's a quotient of polynomials. It's a rational function. And when we do antiderivatives, at the end of the course where you go backwards, right, it's going to be very peculiar because you're going to start with something which is a rational function, right, just a couple polynomials, is x to the minus 1, and it's going to somehow spit out a logarithm. Okay. But one nice thing, there is a little bit of synergy. We do know that, of course, the natural log is only defined for positive numbers. It's definitely not defined at 0. And that's good, because that's not defined at 0 either. You get problems both places. Okay? If we graph ln of x, let's see, what's happening to the slopes as x is getting smaller? What's the slope of this thing? Well, it's getting very steep, yeah? And what about 1 over x? What's the value, what's happening to the values of 1 over x as you get close to 0? It's also going up to infinity. It's getting very big. Okay, so it's matching. The value here is the slope here. So that's kind of, there's a nice little symmetry there. I mean, these are not supposed to be symmetric, but what does that also say? As you go out to infinity, what's happening to 1 over x? Well, 1 over x is getting very small, right? Which means that ln of x, even though it's going up to infinity, the slope is getting smaller. So you can go really, really high, but very, very slowly. This is a reason why in science they use log-scaled graphs. Okay, so what does that mean, a log-scaled graph? Right. Well, let's say you wanted to draw a picture that compared things at our level, you know, desks and chairs, to things in the universe, you know, distances between stars and so forth. Okay, I mean, you couldn't, it would be very difficult to do that to scale, as you might imagine. But if you take the logarithm of everything, well, now what this is telling you is it's going to start to make a lot of sense, because you can keep bigger things bigger right? Because, well, the logarithm certainly gets bigger as you put in bigger x's. But the distance between bigger things gets smaller. Like how big they're getting gets really small as x goes up, because look, the slope is getting really, really small. Right? So maybe I bring in a couple of posters that I found this week that show you can put things on the universal scale, size scale, and a human size scale, and even a quantum size scale, all in one picture, which is not that big. And it can be to scale, as long as your scale is logarithmic. Okay, so what do we got? We have e to the x, and we have the natural log. Okay, that's 2. Okay, but there's a lot more exponential functions, and there's a lot more logarithmic functions. Okay, so let's try to get those out of the way. Okay, so we're going to work this now kind of backwards. So before we started with the exponential, then we did the logarithm. Now we're going to do the logarithms, and then use that to get the last exponentials. Okay. Now to do the next logarithm, all I want to do, I don't want to go back to a limit definition. Okay. If I want to find, so again, we'll let a be greater than 0, and I want to compute the derivative of the log just base a of x. Okay. I don't want to have to somehow repeat all the arguments I've done before. So I want to somehow turn this logarithm back into something that has to do with natural logarithms. Okay. Does anybody remember a way of changing the base of a logarithm? Some sort of formula that changes the base. Oh, the change of base formula. That's very good. Okay. Does anybody remember what it is? Okay. So let's recall. If we'll just do this in general, you say A, B, and C, or A and B are going to be bases greater than 0. Okay. Then the log base b of x. Say I want to change log base b into log base a. Then this is going to be the log base a of x over the log base a of b. Has anybody not seen that formula before? It's actually not hard to prove. I wouldn't prove it in this form. Just a little aside. Okay, to prove this, it'd be the same as if this log a of b was on the other side. So, if you want to prove it, you prove that log base a of b times log base b of x equals log base a of x. And the way to do this is, well, take a and raise it to the log base a of b times log base b of x. Did I get this right, or did I do that backwards? See, if you do it this way, these will cancel, and you get b to the log base b of. Oh yeah, that's right. Okay, good. I did it right. You put some parentheses here. A to the log base a. A and log base a are inverse functions. Okay, so they cancel. So you get just b to the log base b. And of course, b to the log base b, those again cancel, and you get x. Okay, so if you take a and raise it to this power, you get x. On the other hand, clearly, if you take a and raise it to this power, you get x. Since the exponential function is 1 to 1, it must be that these two top terms are equal. Then you divide by this term, and you get exactly this formula. Okay, so it's very easy to prove. Okay, so how do we use that? Well, I want to turn log base A into natural logs, because I already know the answer for natural logs. So this is the derivative of, well, log base A is going to be, well, if I like, log base E, which is natural log of x divided by the natural log of A. I'm just using this formula here. Okay, so this is formula star, and I'm using a star. Okay, so ln is log base E. I just use those interchangeably. Okay, so what can I do with the derivative of ln of x over ln of a? Ideas.
Quotient rule?
Could use the quotient rule, but it'd be overkill. Why is it overkill? Well, when do you use the quotient rule?
Function of a function.
When you have a function over a function, and usually you're talking about a function of x over a function of x. Well, here I have a function of x over a, well, that is a function of x, but it's a very special function of x. If this was a 4, what would you tell me to do? If I just had ln of x over 4, you say pull out the constant, right? Well, a is just a number, so the natural log of a is just a number. So this is just a constant down here. So I can just factor it out. Right? There's no x's involved. Right? This is just a constant. So this is equal to 1 over ln of a times the derivative of ln of x. Right? So no need for the quotient rule in this case. It's too easy. But now we've reduced it to a problem we already know. The derivative of ln of x. Right? We just said the derivative of ln of x
1 over x.
is 1 over x. So this derivative is, well, that's 1 over x. So you get 1 over x ln of a. Okay, so let's record that in a nice little box. The derivative of log base a of x is 1 over x ln of a. So the interesting bit is, even if you are not talking about e, right? Log base a, there's no e involved there. Like a could be 10. You have log base 10. There's no e involved, right? You take a derivative, and that e naturally shows back up. Every time you get it out, it pulls itself back in. Again, though, what happens if a equals e?
Isn't that 1?
Yeah, you get ln of e. ln of e is 1. Okay? And then you recover 1 over x, right? Of course, that's what you should get. If a is e, then this is just ln of x. And the derivative should be 1 over x. So this matches our formula. Okay? All right, now we use this to get all the exponentials. Okay, so we want to know what is the derivative of a to the x. Okay. We have to be tricky. We don't want to go back to the limit definition again. And because remember we ended up at that weird limit at the end. ln of, limit is a to the h minus 1 over h. Right? This was We didn't know what this was. We just knew, okay, if it was 1, that was when A was E, but we didn't know what the limit was going to be otherwise. Okay, so what can we do?
A to the x times derivative of exponent. That's it.
You're saying A to the x times the derivative of the exponent. Well, this is almost the formula. Almost the formula, but we're missing something. We have to account for that extra limit term that we threw in, right? We know the derivative should be A to the x times whatever that limit term was. We called it f prime of 0. But we didn't know what that was. We just said it was some limit. We need to figure out what that term is. So how can we do that? Well, here's the subtle trick. I'm going to replace A by E to the ln of A. Right, which I can do because E and ln are inverse functions. Right? I run the tape, I rewind the tape. Okay, I'm back to A. No problem. But why? Why do that? Well, I know what the derivative of e to the x is. Okay, and so I can use the chain rule, for instance, in this case. So if I reassociate parentheses, this is e to the ln of A times x. Okay, so the derivative of the exponential function, well, we have to use the chain rule here. Okay, derivative of e to the x is e to the x. So I get e, well, instead of to the x, I get e to the ln of A times x, times the derivative of ln of A times x. Now, what should be the derivative of ln of A times x? Okay, easier question. What's the derivative of 2x? 2, right? Because you have a constant times x. Well, remember, ln of A is a constant. It's just a number. So the derivative of ln of A times x is ln of A. And of course, e and ln of A cancel. And so you just get A, so if I put some parentheses here again, this is just A again to the x. So A to the x times ln of A. Aha! This is our f prime of 0. Right? That's our limit of A to the h minus 1 over h as h goes to 0. It's actually ln of A. That's what the number is. Okay? That was the missing ingredient. Okay? So we record that. And it's very much like the logarithm formula. You just throw in this extra ln of A. So this says if you graph A to the x, and you look at the slope of a tangent line, it's again going to have the same slope, only you have to multiply by this constant term. Okay? Which, of course, when A is equal to E, is just 1. It goes away. Okay, so this is very useful. We now know how to handle exponential functions and logarithmic functions to any base. No? Any questions on this? All right, there's a lot of things going on here that we're using. All right, we're using the chain rule constantly. Right? Especially when we start playing these games where, right, we take e and raise it to a y and then we differentiate. Okay, so.
Can we have more practice doing these problems?
Oh yeah, well, of course I'm going to give you a lot of
No.
exercises, but you want me to see an example?
No, right now.
Right now, let's do an example.
Yeah.
Okay, let's do a derivative. Let's do an example. I'm almost out of chalk. This is going to be a real problem. All right, let's find the derivative. Okay, let's start easy one. Okay. e to the x squared plus 3. Okay, nice, easy. Okay, now, the derivative of e to the x is
Yeah.
e to the x, okay? So by the chain rule, the derivative of this function is just e to the x squared plus 3
Okay.
times the derivative
2x.
of x squared plus 3. Okay? Of course, the derivative of x squared plus 3 is 2x. So we get 2x e to the x squared plus 3. Another example. Let's do the derivative, the log base 11 of sine of x. Okay, now we have to be careful here, right? Half of the x's we're not allowed to use, okay? Because sine, right, of course, goes okay, up, down, and when it goes down, where does it go down to?
1.
Yeah, it goes down all the way to -1, right? In particular, it goes between 0 and -1 quite a bit, which means it's negative. Now, when it's negative, what does this log function do? Yeah, it doesn't make any sense, right? So here I'm only looking at the places where the sine function is positive. It can't even be 0, right? It really has to be positive. Okay, but keeping that in mind,
Cosine x.
what do I get? Well, let's see. I have to do the derivative of the outside times the derivative of the inside. Okay, what's the derivative of log base a? Well, it's going to be 1 over the inside ln of a. So 1 over the inside is sine of x times the natural log of a here is 11 times the derivative of the inside. So the derivative of sine of x, which is
Cosine.
cosine. Okay, so I get cosine of x over sine of x ln of 11, which if you like is 1 over ln of 11 times cotangent of x.
So it is the 1.
What's that? You woke up for just a second. Oh. Who's here? You have a question?
Number 1 over there. Is it the derivative for what?
This one? This is the derivative of log base 11, all right? Evaluated at sine of x.
So always 1. I mean,
Yeah, I mean, it's just this formula here.
it can be different, I mean, than 1.
Well, it is what it is. It's a formula. Yeah, I mean, you put a different number here, you have to put a different function here.
Likewise.
Just like, you know, put a different class in here, I have to be a different teacher. Kristen?
I'm confused. Why did you take the derivative of the sine of x there?
Ah, chain rule, right? Remember what the chain rule says. You have a composition of two functions, okay? You have to take the derivative of the outside function and evaluate it at the inside function. So that's what this part is. I took the derivative of log, and I get this, and I evaluated its sine. Then the chain rule says, then you have to multiply by the derivative of the inside function. Okay, so remember the formula for the chain rule. So if you have the composition of two functions, which is what we have here, you take the derivative of the outside function, evaluated at the inside function, that's evaluated sine x, times the derivative of the inside function. And that's why I have to multiply by sine of x. Yep.
Can you just, for the definition, can you just write, what I, like, the 1 over x ln of a times d over dx? Assuming that there will be, like, can you just add that into, like, the little formula?
Okay, so for instance, so a more general version of this formula is to say the following. Okay, so let's say u here is a function of x. Okay, and I want to take the derivative. Use just some function. It could be sine x, it could be x squared plus 3, it could be anything. Right? Then the derivative is 1 over u ln of a times the derivative of u. Okay, that's what the chain rule tells us. U. If u is another function of x, then you get 1 over u. Right? So that's the derivative of log of evaluated at u, right, times the derivative of u. So in fact, all of the formulas that I put up, you can rewrite using the chain rule in exactly this way. So I'll give you an example of that. I mean, I don't know if it helps you any to have those formulas written out there, but if it does, feel free. So, if, let's say u is a function of x, and I have u to the n, and I take the derivative. Okay, this is just the power rule. It says it's going to be nu to the n minus 1 times the derivative of u. Notice that if u is just an x, well, x is a function of x, so this formula should hold for that too. But what's the derivative of x? 1. That's why you don't ever write this term in that case. It's just multiplied by 1. But if u is some other function, boom, that's what you get. Okay. Okay, let's do something else. Since we're talking about the power rule. So let's let now n be any real number. And let's look at y equals x to the n. I'm going to take the logarithm of both sides. So I'll take the log base e. Okay, so if y equals x to the n, then ln of y equals ln of x to the n. Now, I have a rule in this situation I can apply, right? What's ln of x to the n? Yeah, I can take this n and I can move it to the front. So I'll do that. So I get n times ln of x. Okay, now, since this is calculus, and as long as we're here, why don't we differentiate both sides? Okay. What do I get when I differentiate this? Well, I have to use the chain rule, right? So the first step is, what's the derivative of ln? Well, it's 1 over. So I get 1 over y times the derivative of y. Exactly, dy dx. Okay. And what about the other side? What do I get when I differentiate this? I get, well, very good, right? N is a constant, so you don't worry about that. ln of x, the derivative is 1 over x, and then of course you throw this n back in. So you get n over x. Okay, fine. Let me put the y on the other side. Right? So I get dy dx equals yn over x. Okay, now let's see. Y was x to the n. So this is, let me put the n first, right? Okay, n x to the n over x. Okay, I cancel one of the x's. And I get n x to the n minus 1. Ho ho! I started with the function x to the n, and I found that the derivative was nx to the n minus 1. What is that? That's the power rule. But I took n to be any real number.
Oh, so awesome.
This is so awesome, okay? We started off only knowing the power rule for natural numbers, right? We then, okay, we were a little clever, we extended it to integers. And then we were really clever and we extended it to the rational numbers. But now we have it for all real numbers, right? We don't have to pretend anymore, right? We can actually say, the power rule, it works for everything. Doesn't matter what exponent we put up here as long as it's a constant, not a variable. I can stick it up there and bang, zoom, wham, bam, thank you, ma'am, I got a power rule.
Everything makes sense now.
Awesome! Okay. So this is very nice. Okay, let's do a different sort of example. What if I had y equals x to the x? We talked about this situation briefly before. Okay. We said we can't use the power rule. As great as the new power rule we just got, the one that has made Kevin jump out of his seat and scream, huzzah, huzzah! Nonetheless, we can't use it here because why? I don't have a constant exponent. I have a variable exponent. Okay? But we can use the exact same idea as we just used to prove the power rule to attack this problem. Namely, I have an exponent. What did I do in this situation to get rid of an exponent? Well, let's see, I had an exponent, I took a log. Why did I take a log? Because then I can take the exponent, turn that into multiplication. Multiplication is easier than exponentiation. Good stuff, right? So let's do that here. I'll take the natural log of both sides. Right? And of course, by doing that, I do it so I can pull down the exponent. Okay, so there's no more exponents anymore. Fine. This is calculus, so what do? Find the derivative. Okay. So we already know what it is on the left side. Derivative ln of y is 1 over y times dy dx. And what about on the right side? Oh, I have a product. I better use the product rule. Okay, so first say derivative of x is 1 times ln of x, fine, ln of x, plus x times the derivative of ln of x, which is 1 over x, right? So x times 1 over x. Oh, cool. Those will nicely cancel. This is ln of x plus 1. Okay, now I take this 1 over y and I move it over, and I get dy dx equals, well, y times ln of x plus 1. And of course, y was just x to the x. So I get x to the x ln of x plus x to the x.
Class is over, there's no more job.
Okay, so now we can differentiate a bizarre function like x to the x. Yeah.
Wait, so why did you replace 1 with x to the x there?
Oh, well here I had to distribute.
Oh, right.
Yeah. So it's kind of interesting. You actually kind of get the, both worlds put in here. When we did a to the x and you took the derivative, you got, right, a to the x, the derivative was a to the x ln of a. So that's kind of what you would expect from here, right? But then there's this extra term. Now, what would the power rule have told you to do? Well, if you took the derivative here, you would get, and this is of course not real work, x times x to the x minus 1, which is just x to the x again, which is the other term you get. So it's like there's two wrong ways to do this. And the correct answer is to do it wrong both times and add it up, which I find pleasing in some sick way. Okay, let's see another example. Somewhere where this should make things easier. Let's see if there's anything right.
Professor,
Oh, yeah.
the y there, did you divide the x over y or?
So I had 1 over y, and I moved it over, turned it into a y over here. Is that?
Yeah, I mean, this is my question.
And then I replace y with x to the x. And so then it becomes x to the x times ln of x plus x to the x times 1. And is that what you were getting at? Okay. Okay, let's see here. What if I did the cube root of x plus 3 to the 4th over x plus 2 to the 5th times x minus 1 cubed? Actually, I'll square it. Okay, and I said find the derivative. Okay, so what am I going to want to do? Well, okay. I won't be so mean, right? I'll just immediately erase it and turn it into a 1/3 power. Okay, so now it's much easier, right? Okay, I mean, what are you going to have to use? You're going to have to use the chain rule and the power rule. Right? And then you're going to have to use the quotient rule, and oh, it's going to be a mess. Right? Okay, so let's try something else first. What if I take the natural log of both sides? All right, so I'm going to get natural log of x plus 3 to the 4th over x plus 2 to the 5th, x minus 1 squared to the 1/3. Okay, now what happens? I have an exponent. I pull that out. Now I have a quotient. What can I do with the natural log of a quotient?
Subtract.
Yeah, I can turn it into a subtraction, right? That's the beauty. Logarithm is great. It takes exponentiation, turns it into multiplication. It takes division and turns it into subtraction. It takes multiplication and turns it into addition. Okay, it's beautiful. Okay, so let's see. So we get 1/3, and I'm going to get natural log of the top minus natural log of the bottom. Okay, now what else can we do? Well, here I have an exponentiation again, right? So I can pull it to the front. Okay, we start to need more room. So let's see here. I get 4 ln of x plus 3 minus, okay, now I have the natural log of a product. So I can break it up as a sum, right? Turns multiplication into addition. Okay, and when I break it up, I'm going to again get exponents, which I can pull down. So I get minus 5 ln of x plus 2 minus 2 ln of x minus 1. And then 1/3 is hovering around.
Yeah, isn't it plus?
Why is it minus?
Well, you have a minus, and then here you get a plus, but it becomes minus, minus.
Oh.
And whole distributed, well, multiplication and addition. Okay, so we've now reduced it to a rather simple form. And why do I say simple? Well, now let's try to find the derivative. And mind you, if you had a little bit of practice at this, you could actually see how you could immediately rewrite, once you did the ln, you could immediately rewrite it in this form. It wouldn't take long to say, oh yeah, of course, I can Okay, that 1/3 is going to come out first, and you're going to divide, then this one's going to come down, and then this is going to come down, and all these exponents will come down, and it'll become a minus. Yeah, I mean, it's just a little practice, boom, and write it out. You don't need to do it on all these different steps. Okay, so the left side, when we differentiate, it's the same game. You get 1 over y dy dx. And on the right side, okay, we have this 1/3. You put that in at the end. Okay, you have a 4. You don't worry about that. You put that in at the end. Okay, the derivative of ln of x plus 3. Right? Well, let's see. So we'll make the 4/3. We'll put that there. Okay. Derivative of ln is 1 over the function. So 1 over x plus 3 times the derivative of x plus 3. But it's just 1, so I don't worry about it. Then this one, you get minus, okay, 5, and I'll put the thirds. Okay, derivative ln of x plus 2 is just 1 over x plus 2 times the derivative of x plus 2, which is still 1. Minus, okay, 2 over 3. Derivative ln of x minus 1. 1 over x minus 1 times the derivative of x minus 1, which is still 1. Oh, and then we're at the end. Okay? Now to get dy dx, I just move the y to the other side. But of course, I'm going to write the whole thing again with just a y there. I'm going to actually put what y is. It's this function. All right, so it's you have x plus 3 to the 4th over x plus 2 to the 5th times x minus 1 squared to the 1/3 times the rest of this stuff. Right? 4 over 3 times x plus 3 minus 5 over 3 times x plus 2 minus 2 times 3 over 3 times x minus 1.
You gotta simplify those 3, like 3 times x plus 3.
3 times
3 x plus 9 or something.
No, I mean that's not simplified. But
Just wondering.
okay, so mind you, in your head, okay, with just a few little practice, you go from here to there, 1 step. Okay, so you get to skip those steps. Then you write this down. There's your answer. You didn't have to use the quotient rule, right? I mean, again, you vaguely had to use the chain rule, but not in any serious way. I guarantee you, if you wrote that sucker out in full, I mean, you'd be crying by the end, yeah. So this is really a slick way to do it. Okay, so this process.
Wait, I have a
Oh
question.
yeah.
Where did that first term come from, like dy dx? Is
This-
that y?
Yeah. So this
okay.
is. So I took this y and moved it over, and just didn't want to write it down in one more step.
Is this like considered implicit, or is it like another name for it?
I'm going to answer your question at the end of this sentence.
Okay.
This process of first taking the logarithm and then differentiating is called logarithmic differentiation. So this is an extremely useful technique, especially when you get functions of this sort of shape, right? Which, if you were trying to use your chain rule and your quotient rule and everything on it, it's not that you couldn't do it. It's that you have better things to do with your life, I think. So this is much slicker. It's, of course, exactly the same thing we did when we saw x to the x. And so there are two very distinct uses for it, right? One is when you have a function where there's just way too many exponents going on. And two, when you stick variables in the exponents. Right? Because none of our power rule doesn't know what to do with variables in the exponent. We need a way to somehow take the variables out of the exponent, and that is what logarithmic differentiation allows us to do. Let's try another example of it. Let's find the derivative. So let's say, what if I put, actually, I want to put 2x plus 3 to the x sine of x power. Okay, so this is, when your mind is working randomly, this is the sort of dross you can come up with. Okay, so if I call this function y, then logarithmic differentiation suggests that I should take the log of both sides. That is, look at log of y and say this is the same as log of 2x plus 3 to the x sine of x. And of course the reason I do that is exactly so that I can pull this exponent down. So I get x sine of x times the natural log of 2x plus 3. Okay? We did our log business. And after you've done your business and you clean it up, then you, all right, remember we're in a calculus class. Something funny, Kevin? All right, so we're in a calculus class, so we differentiate. Okay, derivative on one side, you know, is 1 over y dy dx. Okay, what about the other side? I have 3 things, right? So I have to use the product rule multiple times. And you can prove, it's not hard, that it generalizes to, the product rule generalizes to 3 terms in kind of the obvious way. Namely, hold 2 of them the same and take the derivative of 1. Then hold the other 2 the same and take the derivative of 1. And then hold these first 2 the same and take the derivative of 1. And add them all up. So let's see. First we'll differentiate x and hold these the same. So the derivative of x is 1. So you get sine of x times ln of 2x plus 3. Plus, okay, now you hold these 2 fixed and differentiate sine, which gives you cosine. So you get x cosine of x ln of 2x plus 3. And then we hold these 2 and we differentiate ln of 2x plus 3. So we get x sine of x times, okay, what's the derivative of ln of 2x plus 3? 1 over 2x plus 3 times the derivative of 2x plus 3, which is 2. Okay, so I'll just put the 2 up here. Okay, so I get this sum of stuff. Okay, and now if I want to know what dy dx is, I just multiply both sides by y, and of course that's my y. So I just have to move it to the other side and multiply it by this sum. And there's my dy dx. Okay, I won't write it down because there's nothing special going on, right? So just take this now and move it to the other side. So this is a really neat way to do things. Any questions on this? All right, well, I have 6 minutes. I could either go through all of inverse trigs in 6 minutes, or we could just do it next time.
We should do it in 6 minutes.
What's that?
I'm ambitious.
Laith wants to do it. Does everybody else want to do it too?
There's like a million of them.
Okay. Well, since I'm effectively out of chalk, why don't we stop for there?